Hi, my name is Julia Vitale, and this is my Physics 2 Lab 2 Lines of Charge. The purpose of this lab was to compare the electric force from the point charge model of the suspending tape from Lab 1 to a line of charges model. The results showed that the charge in the point charge model on each tape was determined to be opposite in charge, with their magnitude equaling 1.8186 e to the negative 8 coulombs. And then in the line of charges model, the charge on each tape was determined to be 2.2 e to the negative 8 coulombs. So as you can see, there's a decent difference between the two charges. The fundamental physics principles used in this lab were gravitational force, which describes the attractive force between any two objects with mass, Coulomb's law, which describes the force of attraction or repulsion between two electric charges, and Newton's second law, which is a system's change in momentum is proportional to the net force applied. So since we are comparing two models, I'll just quickly reference my Lab 1 results. So as you can see here, we calculated that the charge on each tape was 1.8186 e to the negative 8. And as you can see, there's one sphere kind of representing each tape. But in this lab, instead, we're going to have two rows of multiple balls that are going to more effectively represent the charge on each tape. So now I'm going to get into the computational model for this lab. So first I have here just a bunch of constants that we use. This is the mass of one tape, and then this is the estimated net charge on one tape. So essentially for this lab, I first started by plugging in the charge that I got from lab 1, and then from that I kind of plugged and chugged the charge here to get to just formulate the best kind of model that most accurately represented the forces. And the one that ended up working the best for me was this charge here. Okay, and then these are the actual functions of my computational model. So here we're just calculating the E field, and then down here we are essentially creating the lines of charges that I mentioned earlier. And this is the last part of my computational model, which is a superposition, where we're calculating the electric field and the electric force. So as you can see here, they're like the bottom tape here and the top tape, and we're just kind of running through all of this and iterating through in order to create all of these vectors. And this is what my computational model ended up looking like. So as you can see here, this is the top tape, and then this is the bottom tape. And as you can see, we have the white vector is the electric force, which is pointing up, and then the yellow vector is gravitational force, which is pointing down, and then all of these green arrows are the E field. And as you can see here, the magnitude of the electric force is just a little bit larger than the gravitational force, which makes sense because otherwise you wouldn't be seeing that kind of lifting action that we did see. So here are some assumptions and errors that were made. So a few of the assumptions were that air resistance and friction are negligible, each piece of tape has the same magnitude of charge, and that the charge on each tape is uniformly distributed. And then some of the errors that could have been made were that measurements during the experiment were not precise, like we didn't properly measure the distance between the two tapes when we started to notice movement, and then loss of charge due to handling and or the environment. Okay, now moving on to the discussion. The first question is, what if you had modeled each of your tapes as a single point charge? So we did that in the last lab, and you can see that there is a difference between the two charges because the point charge from lab 1 was 1.81 e to the negative 8, and the line charge from this lab was 2.2 e to the negative 8. And then the next question is asking, well, why do these estimates differ? And which one is more likely to be closer to the real value? So the point charge model essentially oversimplifies by treating all the charges as concentrated at one point. But in reality, charge is distributed along the length of the tape so that the point charge model essentially underestimates the force and the charge. So to answer which one is more likely to be closer to the real value, well, it would be the line charge model because it's more realistic as it accounts for the actual geometry and distribution of the charge, making it hence closer to the true value. Thank you so much for watching.